Graphing a piecewise function is basically the same thing as graphing a regular function, but you've got to graph more than one on one Cartesian plane because in different sections there are different graphs. The sections are divided by these breaks. So for example, on the function f at x, there's a section to the left of 1 and there's a section to the right of 1. We have to draw two different lines here. So one method that you can use is you can draw both lines and then erase the section that it's not supposed to be in. So say that we're graphing the function 2x minus 1. That's a linear function with a slope of 2 and a y-intercept of -1. So we would plot 1 here. That's the y-intercept. We'd rise 2, run 1, rise 2, run 1, and maybe go down 2 and left 1. That would give us this line here. If we were to graph the function (x plus 3), that's a slope. It has a slope of -1 and a y-intercept of 3. So we've got 3 here, here, go down 1 and right 1. And so we get this function. And from there, we can erase the sections that it's not supposed to be in. So for example, the graph 2x minus 1 is only supposed to be to the left of 1. So if 1 is here, then this is not supposed to be here. And for the graph (x plus 3), or the line (x plus 3), it's not supposed to be anywhere left of 1. It's only supposed to be greater than or equal to 1. So then we'll erase this portion of the function. There's one more thing to complete. There is a equal to sign for (x plus 3). That means that the function f at x at 1 is wherever the (x plus 3) line is. So you put a solid dot there. But since we don't have an equal sign on 2x minus 1, we have to put a hollow dot here. That means that everywhere just to the left of 1 belongs to this function. So this is the graph of this. Once you have the graph of f at x, you can actually calculate the limit of f at x. So say that I wanted to take the limit as x approaches 1 from the left. Well, we would jump on the function and ride towards 1 from the left. As we get really, really close to 1, you can see that the y value that it approaches is 1. But if we take the limit as x approaches 1 from the right, that means we ride the function from the right and get really, really close to 1. The y value that it's close to is 2. So if I asked you what the limit as x approaches 1 is, or sorry, as x approaches 1, then it doesn't exist because it approaches 1 from the left and 2 from the right. If we want to graph this function, this one's a little bit more complicated because it has 3 different sections. It is the section to the left of -1, the section at -1, and the section greater than -1. Drawing 3 different functions and erasing where it's supposed to be and not supposed to be can kind of become a little tedious, messy, and you might make some mistakes. So we can use a table of values, actually, to get a bunch of ordered pairs and understand how to connect them. So let's create 3 table of values because we have 3 different functions. We'll create one table of values for the function the square root of (x plus 1 minus 1). We'll create another function for x plus 3, or table of values for x plus 3, and we'll create another one for y is equal to x squared minus 2. So for the function, this top function, which is supposed to be only to the left of (1), what x values will you choose? You can choose any values that are to the left of (1). So let's choose -3, -2, and even though (1) doesn't belong to this function, we have to know where to put the hole. So I'm going to put a -1 here and a hole to remind myself that we should be plotting this one not as a solid dot, but as a hole. For the section x is equal to (1), there's really only one x value I should be choosing for this. It's (1). And for the section x is greater than (1), we want to choose values like -1, 0, and 1. Those are all to the right. Again, we had to choose (1) even though it doesn't belong to this function. And we'll put a hole here and a solid dot here to remind us who gets the solid dot. As you sub these all in, you can do that on your calculator. You get the value 0.4. -2 in here is going to create 0. This will create -1. For here, when you sub in, you'll get 2. And then here, you'll get -1, -2, and -1. So if we were to plot these ordered pairs, let's plot the root function. At -3, 0.4, that's about here, -2, 0, and -1, -1. Now, because there's supposed to be a hollow dot here, I'll plot a hollow dot. And then we know that it goes all the way to the left. And remember what type of function it is. It's a root function, so that's how you should be connecting your dots. For the function y is equal to x plus 3, that's really only one dot. It's at negative 1, 2. And finally, for y is equal to x squared minus 2, the parabola, we would get a hollow dot at negative 1, which I won't replot. We get 0, negative 2, so that's here, and 1, negative 1. And because that's a parabola, we know that the shape of the function will go like this. So now we have the complete break function, which we could use to take the limit. So the limit as x approaches negative 1 from the left, as we ride in towards negative 1 on the function just to the left of negative 1, the x value negative 1, what y value does it approach? Negative 1. How about as you come in from the right? As you ride in from the right and get really close to negative 1, it approaches negative 1 as well. So the limit as x approaches negative 1 of g at x, because from the left and from the right they're the same function, it's going to equal to negative 1. And that's despite the fact that there's another dot here. Remember that a limit only answers what the value of x that it's approaching, not what it actually is at that point. These actually have these are both discontinuous functions. We call this, because the function jumped from one to another, a jump discontinuity. I can't spell continuity. And then for this one over here, we're going to call this, because there's a hole in the graph, it's called a removable or hole discontinuity. I'm worried that I spelled removable wrong. I think I did. There's one other type of discontinuity that we'll look a little bit later, and that's an asymptotic discontinuity. But this is how you graph a piecewise function.